It's one of the biggest questions in science. How did life begin on Earth? For decades, researchers have debated whether the key ingredients of life formed right here on our planet, or if they were delivered from space. Now, new research suggests that tiny grains of cosmic dust, drifting across the solar system billions of years ago, may have carried the molecular building blocks that helped spark life on Earth. In a new study published in the monthly notices of the Royal Astronomical Society, a team of scientists from the Diamond Light Source in the UK has found evidence that amino acids, the basic components of proteins and enzymes, could have traveled to Earth on interstellar dust grains. These molecules, such as glycine and alanine, are essential for life as we know it. They form the foundation of biological processes in every living thing. For a long time, scientists weren't sure whether amino acids were born on Earth or came from space. But this study adds weight to the idea that the early Earth may have been seeded with life's ingredients from above. To test this theory, researchers Stephen Thompson and Sarah Day recreated what might have happened billions of years ago. They synthesized tiny particles of amorphous magnesium silicate, a major component of cosmic dust, and coated them with different amino acids, including glycine, alanine, glutamic acid, and aspartic acid. Using advanced techniques like infrared spectroscopy and synchrotron X-ray diffraction, they heated the samples to simulate what happens as dust grains travel through space and warm up near a star, just like they would have in our early solar system. What they found was fascinating. Only glycine and alanine managed to stick to the silicate dust particles. The other amino acids didn't hold on under those harsh conditions. Even more intriguing was what happened next. The glycine and alanine didn't just cling to the dust, they actually formed crystalline structures. Alanine, in particular, remained stable at temperatures well above its normal melting point. And when the researchers tested both forms of alanine, known as L and D-alanine, they discovered that the L form was more reactive. That's significant, because life on Earth primarily uses L amino acids. It suggests there might be a natural cosmic bias toward the forms of molecules that life prefers. The study also revealed that the surface properties of dust grains, such as how much hydrogen they contain, can change how amino acids behave when heated. That means not all cosmic dust is equal. Some grains may have been much better suited to carry life's building blocks than others. These differences could have had enormous consequences for the chemistry of early Earth. Scientists believe that as cosmic dust moved through the solar system, it crossed what's known as the snow line, the point where icy coatings on dust grains evaporate due to the sun's heat. When that happened, amino acids embedded in those icy mantles would have been released, or in some cases, transferred onto the dust itself. This natural filtering process, what the researchers call an astro-mineralogical selection mechanism, might have determined which amino acids survived the journey and ultimately reached Earth. In other words, space dust didn't just deliver organic molecules. It may have selected the ones most likely to lead to life. According to the study, this cosmic delivery likely occurred between 4.4 and 3.4 billion years ago, right when Earth's crust and oceans were forming. And around the same time, the first microfossils began to appear. Evidence from Antarctic micrometeorites and from comets like Wild 2 and 67P/Churyumov-Gerasimenko supports this idea, showing that space rocks are rich in organic molecules, including amino acids. And because micrometeorites were far more common than large comet or asteroid impacts, they might have been the main source of organic material reaching the early Earth, a steady rain of space dust delivering the ingredients for life. This study offers an exciting new piece of the puzzle about our origins. It suggests that interstellar dust grains didn't just carry the seeds of life. They might have played an active role in shaping which molecules survived and made it here. By understanding these cosmic processes, scientists can get a clearer picture of how life began on Earth, and maybe even how it could start elsewhere in the universe. As lead researcher Sarah Day puts it, this work shows the power of combining astronomy, chemistry, and geology to explore one of humanity's oldest and most profound questions. Where did we come from? From cosmic dust to living cells, the story of life might have started long before Earth was even ready to host it.